Hello friend, welcome to Concept Civil. And here today I talk about the limit state of collapse torsion. And this will be the last video regarding IS code. And finally I completed. I made it the whole series of IS code. Along with that we talk about the crack and deflection. This comes under limit state of serviceability. So without further delay, let's get started the last video of the IS code. Okay, so this torsion clauses comes under 41. What they are saying, in structure where torsion is required to maintain equilibrium, members shall be designed for torsion in accordance to 41.234. Such structure indeterminate structure where torsion can be eliminated by releasing redundant restraint. No specific design for torsion is necessary. Provided torsional stiffness is neglected, calculation of internal flows. Adequate control for any torsion cracking is provided with a shear reinforcement. So that means this is by default cover in shear reinforcement. एक चीज तो कम क्लियर हो गया है. What's they saying? But the design rules laid down 41.3 and 4. The clauses may be applied flanged beam substituting BW for B. So these actual apply for where flanged beam, where BW replace in B. And now we talk about the critical section. What's they are saying? Section located less than a distance D from the face of the support may be designed for the same torsion as computed at the distance D, where D is the effective depth. So from here MCQ questions are coming. Now we talk about if shear and torsion is working together. Shear torsion. This is known as your combined shear. Some people are saying. So in that case, the equivalent shear V equivalent equal to VU, that is tau U by BD. No. Sorry. Tau U into BD. Yeah. Plus 1.6 TU by B. TU means torsion. And what is your same thing? What is for your moment and torsion? So in that case, equivalent moment, that is equal to M equivalent equal to MU plus MT, and this MT equal to 1 plus D by B whole divided by 1.7. And now we have to talk about what is capital D. Capital D is the overall depth. 95% place you found D, that is the effective depth. 2-3% place you find the capital D. This is the one significance. The equivalent nominal shear stress tau in this case shall be calculated, that's except for substitution, that's, and same again you find VE. So from here you find three cases: VE less than tau C, V, the case number 1, case number 2, VE greater than tau C but VE less than tau C max, 3, VE greater than tau C max. Again you have to find out that three cases and you have to provide shear reinforcement, because I am saying that shear reinforcement के अंदर ही torsion आ जाता है. Same reinforcement, torsion का reinforcement, longitudinal reinforcement, M, we have to find out M, then 100 ST M equal to, then वो से reinforcement भी calculate हो जाएंगे. ठीक है. This is the formula of transverse reinforcement. Just go through it. I have never seen coming to the any place. Now we talk about the limit state of serviceability. Limit state of serviceability, and we talk about deflection. First, flexure member. In all normal cases, the deflection of a flexure member will not exceed if the ratio its span to its depth, that is the L by D ratio. I have covered L by D for cantilever, for simply supported, for overhang. 7, 20, 26. Not greater than the appropriate ratio. When the deflection is calculated according annexed C, that shall be permissible values. That is all about the deflection. Now we talk about the last things, that is the limit state of serviceability. Okay. If greater than the ratio L by D, then you have to redesign. As simple as that. But आता नहीं है कभी. हाँ, रियल सिनेमा में आ सकता है, बट इन एग्जाम्स नहीं आ सकता है. हाँ, this is crack. What they are saying? In general, compliance with the spacing requirement of reinforcement given this should be sufficient to control flexure cracking. If greater spacing are required, the expected crack width should be checked by formula. Suppose if you find that spacing is 125 center to center, but somehow some scenario you have to provide it 130 mm spacing center to center, so gap is 5 mm. For 5 mm you have to find out what should be the crack width. You have to find out. That is written. If greater spacing are required, the expected crack width should be checked. The formula given in Annexure F. But never you have to use this formula. And what is, so this is for tension member or flexure member. Now 43.2 compression member. What they are saying? Crack due to bending in a compression member subjected to design axial load greater than 0.2 FCK AC. So this is your beam. Bending is happening. So that axial load should be greater than 0.2 FCK AC, where AC is your what? Area of concrete. FCK equal to characteristic compressive strength, and 0.2 is just a number. Yeah, FCK is the characteristic compressive strength of concrete. AC is the area of the cross section of the member, need not be checked. A member subjected lesser load if this is the case 1, this is a case 2, then axial load is less than 0.2 FCK AC, then what happen? May be considered as a flexure member, then treat this particular compression member is a tension member and checked and controlled for crack. Yeah, this is all about your limit states of cracking. So in this last video I talk about the torsion, Then I talk about the shear and torsion, equivalent shear, equivalent moment. When we start the designing, definitely you will find lots of example and that will be very much clear to you. Then we talk about the deflection, limit serviceable deflection and crack. So that with this I am ending this video here, and from next week we started the RCC design topic wise, chapter wise, math wise. जितना डिटेल में हो सके हम बनाएंगे, because people are facing lots of issues there. So till then, thank you for watching this video. If you have any kind of doubt, do comment in the comments. I will definitely get back to you. And yeah, thank you for watching this video. See you next video.